Oh no, the force of interest. This is the force of interest lesson, part one. In this lesson, we'll talk about what is the force of interest and how we can write down the accumulation function and the discount function if we're given the force of interest. Well, let's get started. A lot of students make it through FM without really understanding what the force of interest is. I think you're going to have an easier path if you do understand what it is. So I'm going to kind of walk through this slide here slowly. Hopefully, this one and the next one, hopefully giving you a really good picture in your mind of what the force of interest is actually trying to represent. And I'm going to actually start this discussion by talking about the measures of interest that we've already talked about. Or, in other words, pointing out one thing that you might not have really thought about, and that is that all the measurements of interest in the preceding lessons are useful for measuring interest over specified intervals of time. What were the measures of interest we had? Well, we had the annual effective rate of interest with the annual effective rate of discount, and then we did some nominal rates of interest and nominal rates of discount. Those were useful for measuring interest over specified time intervals. For example, a year, 6 months, quarterly, or monthly. So maybe we had the effective rate of interest per month, right? So that's a period of 1 month. It's also necessary to measure the intensity of interest for each moment in time. Now, is it really necessary? Well, it's certainly necessary if you're planning to pass exam FM, which you are, and it's certainly necessary if you're planning to pass exam MLC. So, yes, I would say it's necessary in that sense. Now, that doesn't mean that if you're doing actuarial work in a normal environment, you're probably not going to be using the force of interest for anything because payments don't tend to occur every single moment. In the real world, payments occur monthly, quarterly, every 6 months, or yearly. And so in those cases, we'll be wanting to use measures of interest for those periods of time. Now, when you're doing theoretical work or you're just trying to understand, or maybe you do have a payment that occurs, for example, every day, and you could approximate that using a continuous rate, then yeah, the force of interest is useful. But I think for most people, even most actuaries in their day-to-day work, they're probably not going to be using the force of interest very often. And even if you work heavily in the financial world, so for example, our MFE instructor, Dr. Michael Yates, has a PhD in quantitative finance. And before I showed him the exam FM syllabus, he had never heard of the term force of interest. So if you're hanging out with your financial buddies and you want to sound really smart, maybe you could throw the force of interest out at them and they probably haven't even heard of it. But back to what it really means. So, as I'm saying, it's necessary to measure the intensity of interest for each moment in time. And that's how I like to describe really small amounts of time as a moment in time. I guess the more precise way to say it, especially if you're talking about in terms of integrals and stuff, it's over, and I really struggle to say this word, so bear with me here, infinitesimally, it's very difficult for me to say, small intervals of time. Basically, just a moment in time. We're trying to now measure the intensity of interest for a single moment in time. And we give the term for this measure of interest for a single moment in time the force of interest. And we denote this with delta. So the force of interest at time t is denoted delta sub t. Now, a couple of points. Delta t is a measure of intensity of interest at exact time t. Okay, so if you want to know the measure of the intensity of interest at time 1, you plug in t as 1. If you want to know it at time 1.1, you plug it in 1.1. And if you want to know it at time at 1.00000001, then you plug that value in, okay? And delta t expresses the measurement as a rate per measure period. And we're always going to assume 1 year. I've never seen the force of interest defined on any other measure except for a year. So 1 year unless stated otherwise, and it's never going to be stated otherwise. So don't worry about that. And so on the next slide, we're actually going to kind of break down what this force of interest is. Okay, so we've established that the force of interest, the purpose of it, is to measure the intensity at a single moment in time. So now let's talk about that for some investment. So let's consider a fund with a balance of capital AFT at time t, right? Capital AFT, remember that's our amount function, so that's the balance of the account at time t. Now, if we think about this fund, really the only thing that changes the fund is interest. So the only force acting on the fund is interest. So this force of interest is the only thing that is changing the balance of the fund, because we're going to assume that this fund has no additional deposits and no withdrawals. So the only thing that's changing the balance of the fund is the force of interest. Now, if we're trying to measure this for a single moment in time, we might think, hey, what about the slope? The rate of change on the accumulation function is measured by the slope. And to find the slope of a curve, we take the first derivative, if you remember from Calculus 1. Now, does that mean the force of interest is just the first derivative of the accumulation function? No, that's not sufficient for the measure of intensity. Why not? Because the measure of intensity must not depend on the amount invested. This is the most confusing part for students. They want to just write down the force of interest as the first derivative of the amount function, but let's take a look at a simple example, and I think you'll understand why you cannot write the force of interest as just that. Let's say we have a particular fund, and one investor invests $1,000 in that fund at time 0, and another investor invests $500 in that fund at time 0. So they're both investing in the same fund, right, at the same time, and the rate of change will be twice as great for the $1,000 investment. So for example, if the fund does really well over the first year, then the amount of interest that the person who invested the $1,000 will be twice the amount of interest that the person who invested $500. And conversely, if the fund does really poorly, then the amount of interest that this guy loses, the $1,000 guy, will be twice that of the $500. So the rate of change will be twice as great for the $1,000 investment. But, this is the key point, but interest is not operating with twice the intensity. They're both in the same fund, so the force of interest is the same for both the $1,000 and the $500 investment because they're in the same fund. The force of interest, the measure of the intensity of the fund at every moment in time, is exactly the same for both of those investments. So we cannot just use the derivative, because the derivative would in essence give us the rate of change at a particular moment in time. How much is it actually changing over that moment of time? And so what we want is we want the measure of intensity, not the rate of change. So we have to divide by the amount invested at that time, just like we divided by the amount invested at that time for the effective rate of interest. Remember the effective rate of interest? Let's talk about the effective rate of interest for a year, for example. We did the amount of interest earned divided by the amount invested at the beginning of that period. That's how we get a rate of interest. And it's exact same thing for the force of interest. When we take the derivative, you can think of that loosely as the amount of interest over the next moment, and then we need to divide by the amount invested at the beginning of that moment, which is the amount of time t. So, here's the payoff. The force of interest is the first derivative of the amount function at time t divided by the amount invested at time t. And because if you write this in terms of the accumulation function, you'll have a k in both the numerator and the denominator, you can also write this as the derivative of the accumulation function at time t divided by the accumulation function at time t. So that's it. That is the force of interest. Key things, it's a measure of the intensity at an exact moment of time, and it's the first derivative divided by the amount invested at time t. Now we're going to try to write the accumulation function in terms of the force of interest. So in other words, given the fact that the force of interest is the derivative of the accumulation function divided by the accumulation function, try to write the accumulation function in terms of the force of interest. Now, if you don't get this, don't worry too much. This is kind of a proof, and you're not going to have to prove anything on Exam FM. The important thing is the formula that we derive from doing this process. But so it's worth trying for yourself, though. So pause the video and give yourself, 5 to 10 minutes to try to write this down for yourself. Okay, so here's what we do. We start with the fact that the derivative, or that the force of interest, rather, is the derivative of the accumulation function divided by the accumulation function. Now here is the trick. We're going to write the right-hand side as the derivative of the natural log. And if you remember how to take the derivative of the natural log of something, it's 1 over that something times the derivative of that something, because you're applying the chain rule. So in other words, if I have the derivative of the natural log of some function, it's 1 over that function times the derivative of that function. And now what we can do is integrate both sides. So I just integrated both sides from 0 to n, and I chose 0 to n because I'm trying to write down a of n. And now on the right hand side, I get to apply the fundamental theorem of calculus. At least I think, if I remember correctly, that's what it's called. But the basic idea is that if I take the integral of a derivative, then I just, whatever I'm doing the integral of a derivative of, I just evaluate that at the bound. So that would be the natural log of a of n, and then minus, at the other bound, the natural log of a of 0. Now what is a of 0? Remember, by definition of the accumulation function, a of 0 is 1, because the accumulation function, a of t, is the accumulated value of an original investment of 1. And the natural log of 1 is 0. So the right-hand side is just the natural log of a of n, which is really convenient because I'm trying to find a of n. So now all I have to do is take the exponential of both sides. And so when I take the exponential of the natural log of something, I just get that something. And so the other side is the exponential of this stuff. So there's my formula. There's my formula. A of n is equal to the exponential of the integral from 0 to n of delta t dt. Do I remember it that way? Definitely not. Definitely not. I remember this equation in words. What does the left-hand side say? Or what is the meaning of the left-hand side? The meaning of the left-hand side is to accumulate money from time 0 to time n, right? That's the purpose of the accumulation function. And so what the left-hand side is doing is accumulating from time 0 to time n. And what does the right-hand side say? Instead of reading the right-hand side as the exponential of the integral from 0 to n of delta t dt, what does this do? When I see this sign here, I'm thinking add up. This is fancy adding. This is adding in the continuous world. So what I'm really doing is I'm adding up the force of interest, and then I look at the bounds of my integral, because that's when I start adding and that's when I end adding. And this is with respect to t, so let delta plug in t as 0. That's the force of interest at time 0. Let t be n. That's the force of interest at time n. So I'm adding up the force of interest from time 0 to time n. That's what that stuff inside the brackets, that's how you read that in words. That's how you read the meaning of that in words. You're adding up the force from time 0 to time n. And then you take the exponential. Okay? Now, this n doesn't have to be an integer. The n does not have to be an integer. It could be 4.5. So for example, if I wanted to accumulate money from time 0 to time 4.5, I would add up the force of interest from time 0 to time 4.5 and take the exponential. So let me read this to you one more time. To accumulate money from time 0 to time n, add up the force of interest from time 0 to time n and take the exponential. It's as simple as that. Well, that works great and everything, but what if my deposit is not at time 0? So what if my deposit's at time t1 and I want to know the value at time t2? So let's let a of t1 comma t2 denote the accumulation factor from time t1 to time t2. So in other words, to accumulate money from time t1 to time t2, you multiply by this factor. And so for example, if I have a deposit at time 2 and I want to know the value at time 5, and then I would multiply by a of 2 comma 5 because I'm accumulating from time 2 to time 5. So now let's try to write this down in terms of the force of interest. Well, basically we want to work with the formula from the previous slide, which always works between time 0 and time n. So if I want to accumulate from time t1 to time t2, I can first discount back to time 0. To discount back to time 0, I divide by a of t1. That has now, in essence, brought the value of that investment at time t1 back to time 0. And then I move it forward to time t2 by multiplying by a of t2. Okay? And now I can just apply the formula from the previous slide to both the numerator and the denominator. Let's start with the numerator. So what do? I want to accumulate money from time 0 to time t2. So I add up the force of interest from time 0 to time t2 and take the exponential. And for the denominator, I want to accumulate money from time 0 to time t1, so I add up the force of interest from time 0 to time t1 and take the exponential. And now I can use a little bit of algebra. I have the exponential of something divided by the exponential of something, and so I can rewrite that as the exponential of the numerator minus the exponential of what's in the denominator, right? And then I can use a little bit of calculus. In essence, I'm adding up from 0 to t2, and then I'm subtracting whatever I added up from 0 to t1. So all that's left over is what I added up from t1 to t2. So this is just the exponential of the integral from t1 to t2 of delta t dt. And again, let's talk about this formula in words. So the left-hand side, as we said, was accumulating from time t1 to time t2. And the right-hand side says, hey, just add up the force of interest from time t1 to time t2 and take the exponential. Really, this is the same formula as the previous slide. The more general way to think about it is if you want to accumulate from some starting time to some ending time, add up the force from that starting time to the ending time and take the exponential. That will give you your accumulation factor for that time interval. Enough with the theory already. Let's work an example. So let's look at an accumulation function example. If the force of interest at time t is 0.15 times the square root of t, and an amount of 5,000 is invested at time t equals 1, what is the value of that investment at time t equals 4? Pause the video, try it for yourself. Okay, so I'm taking $5,000 and I want to accumulate it from time 1 to time 4. And so we use this a of 1 comma 4. And to accumulate from time 1 to time 4 using the force of interest, I take the force of interest and I add it up. I add it up from the beginning time, time 1, to the ending time, time 4, and I take the exponential. So now I'm given the force of interest is 0.15 times the square root of t, so plug that in, 0.15 times t to the 0.5. That's t to the 0.5 is the same thing as the square root of t. And now I just have to integrate. So I add 1 to the exponent, so 0.5 becomes 1.5. I then divide by that new exponent, so I have 0.15 divided by 1.5. And I like to think backwards because taking the derivative is so much easier than taking the integral. So once you've written down your result, think backwards and make sure you get the same thing here. So now if I was taking the derivative of this, I would take the exponent down, the 1.5, and good, now that cancels, and I'm left with just the coefficient of 0.15, and then I would subtract 1 from the exponent. So good, going this direction, I feel good. And now I'm going to evaluate this from 4 to 1. And now it becomes a calculator exercise. So let's use this calculator here. So I'm going to take t to the 1.5, so that's 4 to the 1.5, minus, so hit my right arrow to get out of the exponent, minus 1 to the 1.5, which I know is just 1. Okay, so that's basically everything inside, or my t to the 1.5 evaluated from the bounds is 7. And so I want 5,000 times second e to the x 0.15 divided by 1.5 times 7, which is $10,069. And we'll write that down right there, and we'll put a box around it because that is the answer. Hopefully you're comfortable accumulating money using the force of interest now, but what if we want to discount money? Well, A of t is an accumulation function, right? It accumulates cash flows from time 0 to time t. That's why we call it the accumulation function. And 1 over A of t is the discount function, because if I want to discount money from time t to time 0, I divide by the accumulation function. So let's call that the discount function. So 1 over A of t is the discount function because it discounts cash flows from time t to time 0. Now, unfortunately, they also write the discount function as a to the minus 1 of t. But, you know, it's more common to use that notation to write that for the inverse of a function. But in financial mathematics, it's used to denote the discount function. It's just kind of one of those things. It is what it is. So when you see this, don't think the inverse of the accumulation function. Think the discount function 1 over the accumulation function. In other words, these are equivalent. A to the minus 1 of t is really the equivalent of 1 over A of t. And now, what is 1 over A of t? Well, I know what A of t is. I already talked about this when I talked about the accumulation function. what I'm going to do is if I want to accumulate from time 0 to time t, I add up the force of interest from time 0 to time t and take the exponential. And now because I have 1 over this exponential, I can rewrite this as the exponential of minus the integral from 0 to t of delta t dt, because I can basically, this is exponential is e to the something, and if I have e to the something in the denominator, then it's the same thing as e to the negative that thing in the numerator. Okay? Just simple algebra. So, to accumulate from time 0 to time t, we add up the force of interest from time 0 to t and take the exponential. To discount from time t to time 0, we add up the force of interest from time 0 to t, take the negative, and take the exponential. So that's the only extra step now. If we're discounting, we just add this little minus sign, which makes sense because if we're going to add up the force of interest and take the exponential when we're accumulating, then when we're discounting, we're going to add up, take the negative, and then take the exponential. Just like we did for the accumulation function, now let's talk about the discount function where we're trying to move money from, say, time 5 to time 2. Okay, so let's let a minus 1 of t1, t2 denote the discount factor from time t2 to time t1. In other words, to discount from time t2 to time t1, you multiply by this factor. And of course, we can think about this as 1 over accumulating from t1 to t2, right? Because that's how the discount function and accumulation function are related. They're the inverse of each other. And so now, to accumulate from t1 to t2, we add up from t1 to t2 the force of interest and take the exponential. And using the same algebra as before, it's saying the exponential of minus the integral from t1 to t2 of the force of interest dt. And of course, in words, this says if I want to discount from time t1, or rather discount from time t2 to time t1, so to discount from time t2 to time t1, add up the force of interest from time t1 to t2, add up the force of interest from time t1 to time t2, take the negative. Don't forget to take the negative. If you don't take the negative, then you're accumulating, you're not discounting. So take the negative and then take the exponential. Exercise time. Exercise 1. Pause the video and try it for yourself. Okay, so on July 1st, 1984, a person invested $1,000 in a fund for which the force of interest at time t is given as the force of interest at time t is the quantity, 3 plus 2t divided by 50, where t is the number of years since January 1st, 1984. Right? If I'm measuring this in time, I need to know what time 0 is, and they're telling me time 0 is January 1st, 1984. Determine the accumulated value of the investment on January 1st, 1985. So quick picture. Here's my time 0, 1/1/84, and here's when the investment is made on July 1st, 1984, so my $1,000 invested there. And I want to know the value of this investment on 1/1/85, so let's put a dot there. And just because this is given as a function of t, let's call this time 0, right, because t is measured from January 1st, 1984. And so now this is, I believe, 6 months later, so half of a year, so time 0.5. And then this is 1 year later, so let's call that time 1. So I'm going to take this $1,000 and I want to accumulate it from time 0.5 to time 1. So I multiply by the accumulation function from time 0.5 to time 1. And how do we do that? Do we look back at a formula? No, because we remembered the formula in words. We remembered the formula in words. To accumulate from time 0.5 to time 1, I take the force of interest, right? So I take the force of interest and I add that up. I add that up from the starting time to the ending time. So I add that up from 0.5 to 0.1 and I take the exponential. So now all I need to do is perform the integration. I'm going to factor this 1 out of 50 out of my integral, right? Because I can just take constants out of the integral. And so now I just need to integrate 3 plus 2t. So to integrate 3, well, that's just 3t, right? Because now if I take 3t and I take the derivative of 3t is 3. So the integral of 3 is 3t. And the integral of 2t is t squared, right? Because 2t, bring the 2 down, that's 2, subtract 1, t squared. And the 2 minus 1 is t. Okay, everybody knows how to do that integration. It's very simple. And then I'm going to evaluate this from 1 to 0.5. So evaluate this from 1 to 0.5. And now it is a simple calculator exercise. So let's do that. So I first plug in 1, and I get 3 times 1 plus 1 squared. And then I subtract, plugging in 0.5. 3 times 0.5 plus 0.5 squared. Okay, so that's all that stuff. And then I need to divide that by 50, right? And then I need to take 1,000 times the exponential of that. So 1,000 times the exponential of that, and I get 1,046. So 1,046 is my accumulated value, and so I put a box around it. This is exercise 2. Should you A, just keep watching the video, or B, pause the video and try it for yourself? Of course, B. All right. So exercise 2 says, X is deposited into a savings account at time t equals 0. Great. No other amounts are deposited. The force of interest for the fund is t divided by 30. And the balance of the fund after 10 years is 12,500. Determine the original investment. So basically we're trying to discount this 12,500 for 10 years. That will give us the amount that was originally deposited. So X is 12,500 times the discount function evaluated at 10. That will discount this 12,500 from time 10 to time 0. So what do? We take the force of interest, t over 30. We add that up from time 0 to time 10. That's accumulating. So if we put the minus sign, that would be discounting. And then we take the exponential. Now it's very simple calculus. The 1 over 30 comes out. And then the integral of t is t squared divided by 2, right? Because then if I take t squared divided by 2 and I take the derivative, the 2's cancel, t squared minus the 2 minus 1 becomes t. And so I get 2 times 30 or 60. And so this is minus because I have this minus sign here. So minus t squared divided by 60 evaluated from 10 to 0. So calculator time. And I believe I can do this all in one step. I'm just going to do 12,500 times second e to the x negative. Because when I plug in 0, I get 0. So all I really need to do is plug in the 10. So negative 10 squared, which I know is 100, divided by 60, giving me $2,360.95. $2,360.95. This is exercise 3. Pause the video and try it for yourself. Okay, so 1,000 is deposited into a savings account at time t equals 0. No other amounts are deposited. The accumulation amount in the account at time t is given by, so in this particular problem, they give me the amount function. And really, I could pull off the accumulation function because this is the original investment. Because if I let t be 0, then I get 1,000. So the quantity 1 plus 2t divided by 35 squared, this piece here is the accumulation function, little a of t. You don't need to know that. And we're asked to determine the force of interest at time t equals 32.5. So we want to know the measure of the intensity of interest at an exact time 32.5. Well, let's just write down what the force of interest at any time t is. Well, it's how much is the fund changing at time t, that's the slope, divided by the amount invested at the beginning of that period, which is a of t. So it's the derivative of a of t divided by a of t. And so now let's, for the numerator, we just have to take the derivative of this function. So this constant stays. I bring my exponent down, that's 2. And then I have this stuff, and I take 1 away from the exponent. So 2 minus 1 is 1. And now I have to apply the chain rule. So the chain rule, because basically I was taking the derivative of some function squared. And so the derivative of some function squared is 2 times that function times the derivative of the function. And so this is my function, 1 plus 2t divided by 35. And so the derivative of 1 plus 2t divided by 35, the derivative of 1 is 0. And the derivative of 2t divided by 35 is just 2 out of 35. And then I just write down the accumulation function again for the denominator. So I just write that thing down again. And so now the 1,000s cancel. And I also have one of these in the numerator and 2 of them in the denominator. So this one cancels and I just have a 1 there. And so now I just plug in 32.5. So I get 2 Remember, this canceled, and I get 2 times 35, and then this 1,000 canceled, and so I just plug in 32.5 into this value here, and one of those canceled. So then I just pick up the calculator, and I'm going to use this little handy n over d, and so that's 2 times, I'll use the n over d again. I really like using the n over d because it really allows me to see that what I'm doing on my calculator matches what is on my paper. And so in the denominator, I'm going to have 1 plus, and again, I'll use the n over d, 2 times 32.5, hit the down arrow to get to the denominator, 35, and now I feel really comfortable that what's keyed in here is exactly what's on my paper, giving me 0.04 is the measure of the intensity of the interest acting on the savings account at time 32.5. This is exercise 4, and it's a little bit harder, but go ahead and pause the video and try it for yourself. Okay, so it says a deposit of 1 will accumulate to 2.7183 in 10 years. So if I deposit 1 now, in 10 years I'll have $2.7183, whatever. With a force of interest, this given, determine K. Now the interesting thing about this force of interest is that the function changes between the first 5 years and then the next 5 years. So if we want to accumulate $1 for 10 years, let's first accumulate the dollar from time 0 to time 5 using this force, and then we'll accumulate from time 5 to time 10 using this force. So the accumulation function for 10 years is 2.7183. That's given in the problem. And now we'll use the force of interest for these two factors. And so if I want to accumulate from time 0 to time 5, I'm going to add this up from time 0 to time 5 and take the exponential. And if I'm going to accumulate from time 5 to time 10, then I'll add up this force from time 5 to time 10 and take the exponential. And now it just becomes a calculus / algebra problem. That is, we need to integrate kt. And so k is just a constant, so I'll leave the k. And when I integrate t, I get t squared over 2, and I want to evaluate this from 0 to 5. And now on this one, 0.04k is a constant, so I'll just leave that there. And now I need to integrate t squared, which is t cubed over 3, and I evaluate this from 10 to 5. And so now I just need to do each one of these, and I'll just do them on my calculator here. If I have t squared divided by 2 evaluated from 5 to 0, when I plug in 0, I just get 0. So all I really need to do is 5 squared divided by 2, which is 12.5. So this first term is e to the 12.5k. And then for this next guy, I need to do 10 cubed, hit my right arrow, minus 5 cubed, because I'm evaluating t from 10 to 5. And then I divide by 3 and multiply by 0.04, giving me 11.666666666, go on forever, right? So I'm just going to write that down as 11.667 times k. And so now, because I have e to the something times e to the something else, I can just add those two values. So it's e to the sum of those two. So all I really have to do is take this 11.66 repeating, and I'll add back, and I'll just scroll back up to 12.5. Okay, so I get e to the 24.167k is equal to 2.7183. So really all I need to do is take the natural log of both sides. So the natural log of 2.7183 will be equal to 24.167k. So I'm going to take the natural log of 2.7183, and that's equal to 24.167k. So I'm just going to take that and divide it by the coefficient, and that will give me k, and k is 0.04, let's call that 0.0414. So k is 0.0414.